Good morning, everyone. Thank you for joining us today. In our last deep dive, we really dug into the rise of edge computing, this whole idea of moving intelligence right to where data is born. But that leaves a huge question on the table. How do we actually connect the massive power of the cloud with potentially millions of smart devices out there at the edge? Well, the answer is the network fabric itself. Without a modern, intelligent network, this whole computing continuum is just a bunch of disconnected islands. But with the tech we're about to talk about, it transforms into a programmable superhighway. It's the essential connective tissue that makes this entire vision a reality. So here's our game plan for today. We're going to start by framing the core problem with that data superhighway analogy. Then we'll take apart the first huge building block, 5G, and look at its three very different pillars. From there, we'll see how multi-access edge computing, or MEC, literally brings the cloud right to the network's doorstep. Then we'll look at the brains of the whole operation, software-defined networking, which is what makes this fabric so smart. And finally, we'll see how it all comes together in some really cool real-world applications before we wrap up with the key takeaways. All right, so let's set the stage. The cloud, hybrid setups, the edge, these aren't separate worlds. They're all nodes on one giant spread-out computing map. But their ability to deliver on promises like real-time insights and autonomous action, that depends completely on the network fabric tying them all together. A slow, rigid, or unreliable network makes even the most powerful edge device pretty much useless. So the real challenge here is to transform that potential data dirt road into a genuine programmable superhighway that can handle everything our connected world throws at it. And that leads us straight to the foundation of this superhighway, 5G. Now, I know, to most people, 5G just means faster internet on my phone, but that is barely scratching the surface. Think about it. Every previous wireless generation was built for people, first for voice calls, then browsing, then video. 5G is the first generation that was truly designed from the ground up for machines, for sensors, and for real-time control systems. So to really get it, we have to ask the right question, which is our first big topic. What are the three defining and fundamentally new capabilities of 5G? This table really lays it out perfectly. 5G isn't just one single thing. It's more like a versatile platform that's been engineered to deliver three very distinct kinds of service. You've got eMBB, which is all about pure raw speed. Then there's URLLC, which is totally focused on responsiveness and reliability. And finally, mMTC, which is designed for connecting a massive number of devices. Each one of these pillars is custom-built for a different job that's critical to making that cloud-to-edge continuum work. Let's break each one down. First up is eMBB, or Enhanced Mobile Broadband. You can think of this as the supercharged evolution of 4G LTE, but it's a massive leap in performance. We're talking about delivering incredible bandwidth with peak speeds that could top 10 gigabits per second. This is the pillar that makes things like buffer-free 8K video streaming and truly immersive AR and VR experiences possible. And for businesses, a huge application is fixed wireless access, or FWA. That's where 5G acts as a high-speed alternative to cable or fiber, which is a game-changer for bridging the digital divide. For our continuum, eMBB is the giant, high-capacity on-ramp to the cloud. The second pillar, URLLC, is honestly the real revolution here. It's the biggest leap from previous wireless generations, and it's the key to the industrial edge. With URLLC, it's not really about the highest possible speed. It's engineered for two things: extreme timeliness and rock-solid reliability. It's designed to give wireless control the kind of performance that, up until now, you could only get by plugging in a physical fiber optic cable. This is what unlocks those mission-critical applications where even a tiny bit of delay could have major consequences. And the difference is just staggering. Just look at this chart. URLLC is designed to get the latency, the time it takes to get from a device to the cell tower, down to under 1 millisecond. Compare that to the 30 to 50 milliseconds you typically see with 4G. It's a huge order of magnitude improvement that makes the wireless link feel almost instant. Now, when you pair that kind of speed with 5 nines reliability, that's 99.999% uptime, you've got the tech you need for real-time control systems. This is what takes things like remote robotic surgery and vehicle-to-everything communication out of the lab and into the real world. And our final pillar, mMTC, tackles the other huge driver of the edge, the absolute explosion of the Internet of Things. So if URLLC is all about the quality of one single connection, mMTC is all about the quantity. It's built to support an unbelievable density of devices. We're talking up to 1 million in a single square kilometer. These are usually low-power, low-cost sensors that just need to send a tiny bit of data every now and then. So unlike eMBB, The goal isn't speed. It's all about extreme power efficiency, letting battery-powered sensors last for 10 years or more out in the field. This is the networking that makes smart cities, smart agriculture, and smart grids a reality. So how in the world does one network do all of these different things so well? Well, the secret is in how it intelligently uses a wide range of radio frequencies. Down at the low end, you have sub-1 gigahertz spectrum. This stuff travels far and penetrates buildings well, making it perfect for connecting tons of IoT devices under that mMTC pillar. In the middle, you have mid-band spectrum, which is a great balance of coverage and capacity. It's the real workhorse for most citywide eMBB. And then at the high end, you have millimeter wave. It offers insane capacity and multi-gigabit speeds, but has a very short range, making it perfect for packed places like stadiums or for high-performance wireless internet.
This brings us to a really key innovation in 5G's architecture: network slicing. Basically, slicing lets a mobile operator take their one single physical network and digitally carve it up into multiple, isolated, virtual networks. And each slice can be totally customized for a specific job. For example, an operator could create a high-bandwidth slice for consumers watching videos, a completely separate, ultra-reliable, low-latency slice for an autonomous vehicle network, and a third, super power-efficient slice for a city's smart water meters. This is how one physical network can serve a bunch of different industries with radically different needs all at the same time.
Okay, so 5G's URLLC pillar is fantastic. It solves that last mile of wireless latency. But there's a catch. Even at the speed of light, distance creates delay. That incredible 1 millisecond wireless potential is kind of wasted if your data still has to travel hundreds of miles to a big centralized cloud data center to get processed. The laws of physics are still in charge. So how do we solve that problem? The solution is our next building block: multi-access edge computing, or MEC. This slide shows the value of MEC perfectly. On the left, you see the old way. A device talks to a cell tower, its data then has to go on a long journey across the public internet to some faraway data center, and that takes time. On the right is the MEC way. MEC is all about putting small-scale microclouds right at the edge of the network, often in the same building as the 5G base station. Now look at that journey. It's dramatically shorter. The application is running right there, just one wireless hop away from the device. This creates this incredibly powerful synergy. And the partnership between Verizon 5G Edge and AWS Wavelength is the perfect example. AWS has literally put its servers in storage, what they call wavelength zones, inside Verizon's 5G network buildings. So when a developer puts their app on a wavelength zone, a user's traffic in that city goes from their phone to the tower to the AWS server right there, and it never has to travel over the public internet. This combination of 5G URLLC and MEC is what delivers true end-to-end, single-digit millisecond latency, unlocking a whole new class of apps, like real-time gaming and interactive AR. So we have 5G for fast wireless access, and we have MEC for local compute. But just imagine trying to manage a network that stretches from your private data centers across multiple public clouds and out to thousands of edge locations. It's ridiculously complex. The old way of doing networking, where you have to manually configure every single router and switch one by one, is just too slow and clumsy for this new world. The answer is our final piece of the puzzle: software-defined networking, or SDN. SDN is a fundamental shift in how networks are built. It decouples the network's brain, the control plane, from its muscle, the data plane. In old-school networking, on the left, every router has its own little brain, making its own decisions. With SDN, on the right, all that intelligence is pulled out and centralized into a single software controller. You can think of it like an air traffic control tower for the whole network. It has a complete end-to-end view. The routers and switches become simple devices that just forward packets based on instructions from that central brain. This turns the network from a collection of static boxes into a dynamic, programmable fabric. Okay, let's put it all together. We've got the 3 pillars of 5G for versatile wireless access. We have MEC bringing the cloud right to the edge to crush latency. And we have SDN as the intelligent, programmable control layer on top of everything. Now let's see how this whole integrated system powers some truly next-generation applications. Let's start with vehicle-to-everything, or V2X. Picture this: a car's sensors detect black ice on the road, or a sudden hard braking event. That signal is instantly broadcasted over a 5G URLLC connection. A local MEC server right at the intersection processes that data in real time and then immediately beams out an alert to every other connected car in the area.
This all happens in a few milliseconds, way faster than a human driver could ever see brake lights and react. This is how connected cars can literally see around blind corners.
Or let's think about a smart factory. A private 5G network is a total game changer here. It can replace all those tangled Ethernet cables and spotty Wi-Fi with a single, unified wireless fabric. Using network slicing, the factory can create a dedicated URLLC slice that provides the super reliable, low-latency control needed for precision robots. At the same time, an eMBB slice handles all the high-bandwidth video from AI quality control cameras, and an mMTC slice connects thousands of sensors for predictive maintenance. You get the reliability of a wire with the flexibility of wireless. And these technologies open up other models too. We've mentioned fixed wireless access, which is huge for getting fiber-like internet to places that don't have it. It's also really important to know that 5G complements Wi-Fi. It doesn't replace it. Wi-Fi is still going to be king for indoor connectivity, while 5G is the star for wide-area mobile and mission-critical stuff. And finally, private 5G networks are incredibly powerful for big enterprises like ports or mines that need total control over their network's performance and security. So as we start to wrap up, it's pretty clear that this whole distributed world of hybrid cloud and edge computing isn't just about servers and storage. It's really built on a network that's just as smart, agile, and powerful as the systems it's connecting. The journey from the cloud to the edge depends on the quality of the roads, and we've now officially entered the era of the programmable superhighway. Let's quickly recap the most critical takeaways from today. First, remember that 5G isn't just faster 4G. It's a purpose-built platform with three distinct pillars: eMBB for raw speed, URLLC for real-time responsiveness, and mMTC for massive IoT scale. Second, MEC is the essential partner to 5G. It crushes the latency caused by physical distance by putting cloud resources right at the edge. Third, SDN provides that critical software control layer that turns the whole distributed network into a programmable, automated fabric. And finally, it's the combination of these three, 5G, MEC, and SDN, that creates the superhighway that enables the intelligent real-time applications of the future. I want to leave you with this final thought from our source material because I think it just says it all. Advanced networking is the essential connective tissue that makes low-latency edge and hybrid computing a practical reality. That's the bottom line. It's not an add-on, it's the fundamental enabler of this entire vision. Be sure to tune in for our next deep dive where we'll tackle a crucial topic that builds directly on today's discussion: securing the continuum, the zero trust mandate. Because now that we've built this incredibly powerful distributed superhighway, we have to talk about how we secure it from end to end. Thank you so much for joining us. For more deep dives into the technologies shaping our future, please subscribe to our channel, Tech, AI, and Beyond.